Hello everyone. In this video, I would like to talk about how we can approximate an integral by using Riemann sums. So the first thing to remember is a Riemann sum. We're going to take our interval and we're going to divide it up into subintervals. And in each subinterval, we're going to have a rectangle. The width of the rectangles, they can be different, meaning the width of our subintervals can be different. And we can actually use any point within that subinterval to help us find the height of each rectangle. We'll find the area of each rectangle, we'll add all those areas together, and that's going to give us an approximation for the integral. So I want to do this by taking a look at a specific example. So my example, approximate the integral from 0 to 5 of the square root of 25 minus x squared times dx by partitioning the interval 0 to 5 into 5 subintervals, each of length 1. So just right away, we can verify that. So if I take my entire length here, so if I do 5 minus 0, that gives me the entire length of my interval, is 5 units. And I want to divide that up into 5 subintervals, so each one will be 1 unit long. So our subintervals are going to be from 0 to 1. We're going to have from 1 to 2, 2 to 3, and so on. So those are the 5 subintervals we're going to be working with. And I want to take a look at the 3 most common Riemann sums. The left Riemann sum, which means we're going to be using the left endpoint of each subinterval. The right Riemann sum, which means we'll be using the right endpoint. And the midpoint Riemann sum, which, exactly like it sounds, we're going to be using the midpoint of each subinterval. And then this function, it is actually a semicircle. So then let's finish up by using geometry to find the exact area so we can compare. So let's begin with our left Riemann sum. So the left Riemann sum, and we're going to be using our intervals again of 0 to 1, 1 to 2, 2 to 3, and so on. All right, so our general notation, we do start with sigma to represent the sum, and we're going to go from I is equal to 1. And in this case, we're using 5 subintervals, so we're going up to 5. And then our notation we use for this, f of u sub I. So this represents the height of each of these rectangles. U sub I can be any point within each of these subintervals. For a left Riemann sum, it's specifically going to be the left endpoint. So it'll be 0, 1, 2, 3, and 4. And then we're going to multiply that by delta x sub I, which is the change in x, which is the width of each of the subintervals, or the width of the rectangles. And for our scenario, each of our subintervals has a width of 1, which is going to make this pretty simple. So let's write this all out. So we're using the left endpoints. So we're going to be doing f of 0. And I'm going to put this in brackets because our delta x sub I is the same for all of these subintervals. I'm just going to put that at the end. So basically, I'm factoring that out. So you have f of 0, f of 1, f of 2, f of 3, and finally f of 4. And all of these are being multiplied by the width of each subinterval, which in this case is actually just 1. All right, so now let's evaluate what we have here. And this is going to give us our approximation. So f of 0, if I plug that in, I just get the square root of 25, which is 5. If we plug in 1, it's going to be 25 minus 1, so that's the square root of 24. If we plug in 2, so 25 minus 2 squared, it's going to be the square root of 21. F of 3, it's going to be 25 minus 9, which is going to be the square root of 16, which is 4. And then the last one, we have f of 4, so 25 minus 16, that's going to be the square root of 9, which is 3. We can do a little bit of simplifying. 4 and 3 and 5, that's going to be 12, plus the square root of 24, plus the square root of 21. And why don't we get a decimal approximation for this? And our decimal approximation is 21.482. So an approximation for the area underneath this semicircle from 0 to 5. So that was the left Riemann sum. Let's go through the same process with the right Riemann sum. So again, just to jot down our intervals, 0 to 1, 1 to 2, 2 to 3, all the way up to 5. And our notation, so we have sigma, I is equal to 1, and we're going up to 5 because we have 5 subintervals. And we have f of u sub I. And in this scenario, each u sub I, since we're doing a right Riemann sum, will be the right endpoint. And we're going to multiply by delta x sub I, which, again, for us is going to be a width of 1. And each subinterval has that width. So we have our right endpoints. We have f of 1, f of 2, plus f of 3, plus f of 4, and finally plus f of 5. And each of these would be multiplied by delta x, which is just 1. So let's see what we end up in this case. So 25 minus 1, we have the square root of 24. Some of these are repeats from our left Riemann sum, so it saves us a little bit of work. Square root of 21, f of 3. So if we do the square root of 16, that's going to be 4. This one ended up being the square root of 9, so that's 3. And then our last one is new. So if I plug in 5, 25 minus 5 squared, we actually end up with 0. So the square root of 0 is 0. So here we end up with 7 plus the square root of 24 plus the square root of 21. And let's also get a decimal approximation for this. So in this case, it is actually just 5 less than what we had for the left Riemann sum. So that's going to be 16.482 square units. The last Riemann sum we wanted to find was using the midpoint. So let me just jot down our intervals again. And now for the midpoint Riemann sum, we are going to be using the midpoint in each of these subintervals. So the midpoint between 0 and 1 is going to be 1/2. In between 1 and 2 will be 3/2. Here we're going to have 5/2, and so on, 7/2, and lastly 9/2, or 4.5. But now for our Riemann sum, the setup is going to be exactly the same. So we're going from I is equal to 1. We have 5 subintervals, f of u sub I. U sub I in each case is going to be the midpoint, multiplying by delta x sub I, which in this example is going to be 1. So writing out our sum, we have f of 1/2 and f of 3/2 and the rest of the midpoints. All right, and now evaluating our function for each of the midpoints. So plugging in 1/2, so it's going to end up being 25 minus 1/2 squared, or 25 minus 1/4, and then we're going to have the square root of that. So that's going to end up being the square root of 24 3/4, or 24.75. If we plug in 3/2, same process, we end up with 22 3/4, and the square root of that. If we plug in 5/2, that's going to give us the square root of 18 3/4. If we plug in 7/2, we're going to end up with the square root of 12 3/4. And our last one, if we plug in 9/2, it's going to be 25 minus 9/2 squared, which is 81/4, or 20.25. So 25 minus that, we end up with 4 3/4, and it is the square root of that. And all of these would be multiplied by the width, which is 1. So I'm going to get a decimal approximation of this so we can compare it to our other two Riemann sums. So getting a decimal approximation, we end up with an approximate area of 19.825, and rounding that to 3 decimal spots. If we just go back and compare that to the other two approximations. So this was 19.8 about. Here we had 16.5. And this one was about 21.5. Now let's finish up by comparing this to the actual area by using a little bit of geometry. So first, if we graph this function, we can see that this is just a semicircle. The semicircle is going to have a radius of 5, and we are only going from 0 to 5. So I only have to worry about what's in the first quadrant here. So from 0 to 5. And then, so this is going to be the radius. So we have a point here, so it crosses or touches the x-axis. On the y-axis, we're going to go up to positive 5, which is also going to be the radius. And now we have this semicircle. I'm going to do my best job of drawing a nice smooth curve here. So it's a semicircle with a radius of 5. Because we're only looking at the interval from 0 to 5, we are just looking at a quarter of a circle just in the first quadrant. So the area is going to be equal to, so pi r squared would give me the area of the entire circle, but we're only looking at a quarter of it, so we'll divide this by 4. So pi times the radius squared, so pi times 5 squared, we'll divide that by 4. So the exact area is going to be 25 over 4 times pi, which approximately is about 19.635 square units. So again, just quickly going back to what we ended up with for our other Riemann sums. So the exact area, 19.635. Here we had an area of 19.825, so that one was actually pretty close. Here, 16.482, so a little bit less than what the actual area is. And here, 21.482, a little bit more than what the actual area is. But using Riemann sums, we can get an approximation, and as we saw, one of them gave us a pretty close approximation. And the other thing to note, as we've been seeing in calculus, the more subintervals we use, meaning the more rectangles we use, the closer and closer this approximation is going to get to the exact area.